Hi everyone, my name is Chris, and I'm here to present our paper, A Study of the Power of Heuristic-based Pruning via SAT Planning. This is a joint work with Pascal Bercher and Charles Gretton from the Australian National University. As a brief outline, our work is a study of a hybrid approach to planning, in which we use SAT encodings of both the planning problem and the heuristic itself in order to prune the search space. I'll take you through exactly what this all means and how useful it turns out to be in practice. Here's a simple deterministic planning problem that we'll use as a running example. A 3-story building with an elevator and 2 passengers, and our aim is to board and onboard them to get them all to their destination. We first capture the various states of the problem by defining some variables. Each variable has an associated set of values that represent their domains, and using this we can define the initial state and the goal conditions. We'll be referring to variable assignments as facts, and we can define a state as a set of facts, one for each variable. After that, we can describe the actions that take us from one state to another, like this. Each action has a set of preconditions that must be true beforehand, and a set of effects that will become true afterward. This should be enough information to capture the planning task as a whole. Note that this is the SATs plus definition of a planning task, and there exists others, such as the commonly used strips formalism. Here's a small section of the state space for the elevator example, with dots representing the passengers. If we wanted to find a goal state from the initial state, one idea is to do some kind of forward search through the state space. Better yet, make the search more efficient by using a heuristic to estimate how far away each state is from the goal, allowing us to make more informed decisions about which states to explore first. But an entirely different idea, and the one that we're concerned with, is solving the planning problem by first transforming it into a different problem, one that we can solve fairly easily using existing general-purpose algorithms. In our case, this problem is Boolean satisfiability, or SAT. We need to transform our planning problem into a SAT problem, such that a valid plan is obtained by solving it using a SAT decision procedure. There exist many ways of doing this, but we used what's called the direct encoding. The Boolean variables that we'll use are split into 2 groups, action variables and fact variables. Action variables represent whether or not a particular action is executed at a given time step. Fact variables represent whether or not a variable is assigned a particular value from its domain at a given time step. Note that, because we need a Boolean variable for each action and a fact for every time step, it's necessary that our planning problem is a bounded one so that we can deal with a finite number of variables. We end up using this bound as a key element to our methodology later. So with just these 2 types of variables, we can come up with a series of SAT clauses that capture the rules of our original problem, such as the initial state must hold at time step 0, and the goal conditions must be met at the final time step, capital T. And if an action is taken at step T, then its effects must hold at the beginning of step T plus 1, and so on. I won't go through all of them here, but feel free to check out the slides later if you're interested. The conjunction of all of these clauses form the clause set HT. We can solve this using traditional SAT solving methods to obtain a satisfying assignment for each Boolean variable. Then extracting a valid plan is as simple as taking the action variable at each time step that's assigned as true. But this method is nothing new, and not exactly what we're interested in. We want to take this idea of encoding a planning problem in SAT and use it in a slightly different way. In a 2011 paper by Yossi Rintanen, he puts forward the idea of implementing admissible heuristics in SAT. The aim is to find a way to identify states where the heuristic value tells us that you cannot reach a goal from that state before hitting the horizon bound first. So his definition is, if a heuristic is implemented in SAT, we take our base encoding HT, a heuristic encoding chi-t, and any state at some time step, and combine it together. If we then perform a limited solve on it, and we find that it's unsatisfiable, then it is impossible to reach a goal from that state before hitting the search bound. As an example, here we have a state at time step 3 and a goal at 7, with the horizon bound at 6. We don't know that the goal is at 7 yet, so for all we know we can still reach it. However, because we're using an admissible heuristic, which always underestimates the distance to the goal, the heuristic value for the state says it's going to take at least 4 steps to reach the goal. Thus we know that this state is doomed to hit the horizon first, as it's only 3 steps away. From the SAT point of view, if we've implemented the heuristic, every single state that is doomed in this way will result in a contradiction after doing a limited solve in SAT. Now by limited solve, we're explicitly talking about unit propagation. This is a simple and fast procedure that takes clauses with only one variable, assigns it the only value possible that makes a clause true, and propagates this information throughout every clause to simplify the formula. There are no additional steps to solve the problem for this definition to work, just a quick check with unit propagation to see if the empty clause is derived, and that's it. One important theorem that arises from this work is that if a heuristic has been implemented in this way, solving the problem by the standard SAT workflow can simulate the iterative deepening A-star search within the same time and space bounds. This is due to unit propagation providing earlier backtracking than is possible with IDA star. He also shows that it's possible to construct a planning problem such that A star and IDA star take exponentially more computation to find a solution than the set-based approach, given that the search uses the same heuristic as the implemented heuristic. We'll revisit this later. So how do we go about actually implementing some heuristics in SAT? Let's take Hmax, which uses the length of the path to achieve the most expensive subgoal as an estimate for obtaining all of the subgoals. Well, one interesting consequence of this definition is that the base encoding HT actually already implements Hmax, and no further work is needed. If you're interested, there's a proof for this in the Rintonen paper that we won't go into here. However, for other heuristics, things aren't so simple. Let's take the HM family of heuristics. It's similar to Hmax, but instead tries to find the most expensive set of M subgoals instead of just one. So you can think of Hmax as a part of this family, it's basically just H1. We need an actual encoding for this as we don't get it for free. So in a 2012 paper by Jimbo Huang, he puts forward one such encoding for the HM family of heuristics in SAT. For this encoding, we need a type of variable called a metafact for every possible set of facts between a size 2 and m, implying the truth of those facts. Using this, the encoding consists of 4 types of clauses, as follows. Type 1 clauses just ensure that if a metafact is true, then so are all the facts that it represents, and vice versa. The next 2 are significantly more complex and are coupled quite closely, so here's one way to paraphrase them. If a set of facts have gone from false to true, this means that at least one action that applies to these facts, a subset of facts of a size at most m obtained from regressing that action must be true. You can just think of this as a way to ensure consistency when using these metafacts, regressing through the state space and keeping an eye on sets of facts and how they change. Finally, with type 4, we end with the metafact equivalent of the goal state conditions. And all of these together create our heuristic encoding for HM. Now, while this encoding has been described and proven correct by this paper, it hasn't to our knowledge been implemented before, so this was our first novel task. Now, the glaring question that I finally get to answer is, why is this useful? What can we do with a SAT implemented heuristic? Well, let's say we're in the middle of some kind of bounded forward search. The base encoding and heuristic encoding can be generated before the search, as the information captured by these stay the same throughout. If we then use the current state that we're looking at as a set of assumptions to add to this encoding, creating this formula from earlier, all we have to do is perform some quick unit propagation on it, and we have the potential to find that searching from that state is useless. This means that if the UP results in an empty clause, we know for sure that the goal cannot be found before hitting the horizon bound, and thus we can immediately prune the state from the search. Better yet, because this process is so incredibly fast, we can afford to do this every single time a new state is discovered by the search, cutting out a significant portion of the search space. Of course, there are 2 big variables at play here that can make or break this method. 1, the more accurate the heuristic is, the better the potential is for pruning more of the search space. 2, and this is a big factor, will the time spent generating the base and heuristic encodings overshadow the efficiency gains we get from pruning? This is one of the main questions that we try to get the answer to in our empirical study. Note that because we need a bounded search in order to create the set encodings, we take a particular interest in the IDA star search algorithm, which gives us a strict bound for each iteration of the search. Also, by getting a collection of admissible heuristic estimates on the initial state before the search starts, we can pick a starting bound as the maximum of these because of admissibility, which is a bit more strategic than just starting at 1 for every search. Finally, it could seem strange at first that using the same heuristic for search and pruning results in fewer expanded states than using only the search heuristic, because surely the states that get pruned would not be visited in the first place. Well, for one explanation, there's the case where UP actually manages to solve the entire SAT formula, allowing the search iteration to end prematurely. The other stems from the fact that we perform UP on both the heuristic encoding and the encoding of the entire problem itself. This means that the pruning procedure has access to more information than the search heuristic alone, and can potentially result in states being pruned for reasons that the search heuristic is not aware of. So here's how we set up the experiments. We took the planning system fast downward and the SAT solver mini-SAT, combined them together, and modified them to make use of our hybrid search approach. We do all the SAT clause generation in fast downward, including the first known implementation of the HM SAT encoding. These SAT clauses are then generated and passed to the SAT solver before the search begins. And because we're making use of an incremental SAT solver, we just have to do this once, and simply feed it a new set of assumptions whenever we find a new state to do unit propagation on. If the result is unsatisfiable, we can immediately prune this state as it's doomed to fail. If it's satisfiable, then we luckily manage to solve the entire problem with just one UP call. This is fairly common for smaller problems, but grows increasingly rare as problems become more complex. Finally, if the result is neither a solution nor a contradiction, found purely from UP, then we just continue the search as usual. So in order to test this out, we took a collection of 24 well-known planning domains and gave our software 30 minutes to solve as many problems as it could for each domain. There are only 15 of these domains proved to yield any useful results. These experiments were split into multiple groups based on what search algorithm and search heuristic is used. Here are the first two groups of experiments, which both use IDA star, but one group searches with Hmax and the other with H2. Now remember that we're talking about two kinds of heuristics here. The search heuristic, which is used for choosing which states are to be searched next, and the prune heuristic, which is used by our SAT procedure to determine which states are doomed to fail. These can be the same or they can be different. In each of these plots, I'm showing just two of the tested domains, blocks and philosophers, and problems get harder left to right. The solid triangle is always no pruning, which is what we're attempting to beat, and the square and star are our two pruning methods for Hmax and H2 respectively. Here we see that our pruning is working as planned, resulting in way fewer states explored in the search. These are all log plots too, so if we look at problem 18 in the blocks domain, the difference between no pruning and H2 pruning is actually around 24 million states. Also cool to see that H2 seems particularly good for the blocks domain, however you can probably notice that pruning is solving fewer problems. And here's why. It is showing time in seconds instead of states explored. For Hmax search, both pruning methods end up taking longer than the baseline approach. This shows us that for this particular search heuristic, generating the SAT clauses just isn't worth the effort for what we get in return, purely because it takes too long for it to matter. Now things change a bit when we use H2 for our search heuristic instead. Pruning is doing its job like before, but this time H2 is actually managing to solve an extra problem in the blocks domain. An interesting quirk that arose in this case was that a small subset of problems would actually have more expanded states when using pruning, like blocks problem 9 here. This is naturally because a smaller search space does not necessarily guarantee being able to find a goal earlier. If we then look at time, pruning's generally doing a lot better than the baseline approach, especially H2 pruning, and you can see this is the case for both domains here. In these two groups of experiments, we can test our theory from earlier for when the search and pruning heuristic are the same. It seems that the exponential separation that we wanted to see unfortunately does not occur in our hybrid approach, and even results in consistently slower solve times. On the other hand, the same comparison for the H2 heuristic shows that there could be an advantage to using our approach, and though the separation may not be exponential in practice, there's still a noteworthy performance gain. The third group is an odd one, which tests how well this pruning approach fares when using generally high-performing search parameters. In this case, a greedy search using the FF search heuristic. Does this change anything? Well, it appears that pruning is working well if we look at the number of states searched, especially with H2 managing to solve an extra 2 problems in blocks. But blocks is actually the exception. Pruning is otherwise consistently worse than no pruning in this case, and most other domains look more similar to the philosopher's plot here. As an insight to why this overhead is so significant, here you can see just how large these SAT formulae are getting. The majority of the clauses come from the heuristic encoding alone, which accounts for the large difference between the Hmax and H2 formulae. It's no surprise that most of the runtime is spent generating this before the search even begins. So what does this tell us overall? Well, our hybrid pruning approach is useful in a few cases, like when we're using H2 as our search heuristic, or the blocks domain being a peculiar case which seems to lend itself quite well to this method. However, in a lot of cases, it's not particularly worth doing, as all of the things you have to do in order to power the SAT-based approach end up overshadowing the performance gains we get in return. This is unfortunate, but the story doesn't have to end there. This idea can be expanded in many different ways, such as more intelligent ways of changing the bound, or implementing other heuristics in SAT, or even utilizing different bounds than just the search horizon. Something stronger than unit propagation could prove to be useful without increasing the overhead too much. And finally, there could simply just be a better way to generate these SAT clauses, as there exist other encodings than what we've used here. Thanks for coming to this talk. We're happy to take any questions you may have.